Carbon fiber reinforced polymer is an advanced composite material, often referred to as carbon fiber, even though technically this would be the name of the compound or matrix used to create the composite CFRP, carbon fiber reinforced polymer. There are several chemical properties of carbon as an element before it is a compound, let alone a composite. First and foremost, carbon when combined with oxygen creates carbon dioxide and carbon monoxide. It has a melting point of 3,825 degrees Celsius, which proves its high heat tolerance. Carbon has the ability to create long strings or chains of atoms, and carbon actually forms more compounds than all the other elements in the periodic table combined. In diamond form, carbon actually has a density of about 3.153. And in graphite form, 2.2. The carbon element has physical properties such as the following. In diamond substance, it has high transparency, is actually one of the hardest substances known to man, and has low conductivity. In graphite form, it is opaque and black in color. It is normally soft and is used often as pencil lead, and quite to the contrary with a diamond substance, it is a great conductor. Carbon fiber as a compound is a material consisting of fibers, about 5 to 10 micrometers in diameter, and is composed mostly of carbon atoms. Carbon fiber is normally combined with other materials to form a composite. An example of one is that CF combined with plastic resin equals to CFRP, which is the advanced composite material of our discussion. Carbon fiber reinforced polymer is an extremely strong and lightweight fiber reinforced polymer that contains carbon fiber compound as its matrix and polymer its reinforcement. CFRP could be expensive to produce, to say the least, but are very commonly applied whenever high strength to weight ratio is required, such as automotive engineering, aerospace, sports good, etc. The binding polymer, which is the reinforcement of carbon fiber reinforced polymer, is often a thermoset resin, which is a petrochemical that irreversibly cures, which may be induced by heat, typically above 200 degrees Celsius. These resin may include epoxy, vinyl, nylon, or polyester. The molecular structure of carbon fiber forms a hexagonal graphite structure, chained or linked by carbon atoms. It has properties such as low heat expansion ratio and high tensile strength. PAN, or polyacrylonitrile, is a crucial ingredient in carbon fiber and has no density, harsh texture similar to horsehair, thermal stability, high strength, a modulus of elasticity, and high tensile strength. More about polyacrylonitrile. It has a chemical covalent bond and is a double bond because it is made of monomers. Furthermore, above is a molecular structure of PAN. As to how carbon fiber is formed, 90% of carbon fiber is PAN and 10% is petroleum pitch, all organic polymers. It's strings of molecules bound together by carbon atoms. The process of making carbon fiber is part mechanical and part chemical. The precursor is later heated to a very high temperature without allowing contact with any oxygen. This is so that the fiber will not burn. The high temperature causes the fiber to vibrate violently until most of the non-carbon atoms are expelled. There are typically 5 segments in the manufacturing of carbon fibers from the PAN process. These are, first, spinning, PAN mixes other ingredients and spun into fibers, which are then washed and stretched. Next is stabilizing, chemical alteration to stabilize the bonding. Then carbonizing, stabilize fibers heated to a very high temperature, forming tightly bonded carbon crystals. Treating surface, surface of the fibers are oxidized to improve bonding properties. And 5, sizing. Fibers are coated and wound into bobbins, which are then loaded to spinning machines that twist the fibers into different sized yarns. Instead of being woven into fabrics, fibers may be formed into composites. To form composite materials, heat, pressure, or a vacuum binds fibers together with plastic polymer. There are several notable benefits of using carbon fiber reinforced polymer within automotive engineering. First and foremost, to replace the steel components of a car, which just about takes over the whole outer body of the vehicle, with carbon fiber, the weight of the car would be able to reduce up to 60%, and this would result in 30% less fuel consumption. This leads to the reduction of greenhouse gas emission by 10 to 20%. With even just the outer body of the car replaced by this thin, lightweight artificial fiber, the weight of the car will significantly reduce and allow more room for the development of other engines, such as electrical engines, which could further decrease greenhouse gas emission. This will then solve the issue of oil crisis and global warming caused by the excessive use of fuel or gasoline-based motors. And lastly, as for the main concern, that is the endurance this material possesses for its otherwise light property, CFRP is not only 5 times as strong as steel, but 2 times as stiff and rigid, with the added benefit of being 2/3 its weight, hence its reputation in providing a record-breaking strength-to-weight ratio for such an advanced composite material. As to why a technology that seems to have limitless benefits is not currently in widespread use, it is all truthfully a matter of pricing. Certain sports cars known to have only several body parts carbon fiber share the commonality of being rather outrageous in price, and majority would start above $100,000. 10 years ago, the price of carbon fiber per pound was $150, and now it has been reduced to $10 a pound. Even so, a pound of steel costs less than $1. A reduction of $5 a pound in carbon fiber would be needed in order to conduct even the slightest chance of this material be widespread. Nevertheless, a couple more years could surely reduce the price of this fiber, providing hope. However, the limitation of this material does not end economically. Another obstacle standing in the widespread use of carbon fiber is its waste disposal. Typically, cars that have broken down would be recycled through the melting of scrap steel, and that would then be used to make another car or any other object made of steel. Carbon fiber, on the other hand, cannot be melted, and recycling this fiber is not as simple. And even if the material will be recycled, its strength will significantly decrease from its previous use, and would be proven to certainly not be strong enough to construct a new car. Having more carbon fiber vehicles would in fact reduce oil use, however, it would generate a lot of waste. In conclusion, the widespread use of carbon fiber in automotive vehicles might be questionable due to it solving one global crisis and raising another. Nonetheless, only new discoveries and solutions will tell how this advanced composite material will be benefited in the automotive industry.